In this video, let us derive equation of motion of Atwood's machine using Lagrange's equation of motion. Now let us start by discussing what is Atwood's machine. Atwood's machine is a very simple setup which consists of a small pulley with two masses connected by a weightless rope, and this rope runs over the pulley. This simple arrangement is called Atwood's machine. This was first invented by George Atwood, a mathematician belonging to 18th century, to illustrate or to demonstrate Newton's law of motion in classroom. But this simple device forms the laid the foundation for inventing elevators. The elevator works on the principle of Atwood's machine. Not only the elevators, rope cars, sky lifts, winch cars, all these works on the principle of Atwood's machine. To me, whenever I come across the word Atwood's machine, I think of my childhood days fetching water from the well. So we have a pulley. You have a pulley and you will have a rope. On one end you will have a bucket. Other one you will pull the rope. So this setup is. I feel this setup is based on the principle of Atwood's machine. Okay. Now let's derive the equation of motion of Atwood's machine. For this problem, let us take two masses m1 and m2 and let us connect it by an inextensible rope of length L, which runs over a very small, massless and frictionless pulley. So this is the Atwood's machine which we have used here, which we have taken for this problem. See, you have a pulley here. In one end you have mass m1, on the other end you have a mass m2, and L is the entire length of the string. So let us take the mass m1 from the mass m1 at a distance, vertical distance x from the pulley. So we know total length of the string is L. So mass m1 is at a distance x, then the remaining distance L minus x is the vertical distance of mass m2 to the pulley. Next, what is the constraint involved here? It is in holonomic. This system is coming under holonomic constraint, and it is a conservative system where the total energy is a constant. If the pulley used is smooth and frictionless, scleronomous constraint is also involved. That is, the time independent constraint is also involved here. Then degrees of freedom. Here the motion is restricted in only one direction. Hence we need only one coordinate to explain this system. So the system depends upon only one coordinate. So the degrees of freedom is 1 here. Okay. Next, let us find out the velocities with which the masses m1 and m2 are moving. We know the expression for velocity v is equal to dr by dt, where r is the distance. Here this distance for the mass m1 is x, so dx by dt. So one time of differential in classical mechanics we write it as x dot. Then velocity v2 d by dt of L minus x. So the mass m2 is at a vertical distance of L minus x from the pulley. So in place of r we write L minus x. So this is the velocity with which the mass m2 is moving. So here d by dt L minus x, since L is a constant, differential of that will give you 0. So which is left is minus dx by dt, which can be written as minus x dot. Now next let us find out what is the kinetic energy of the system. We know the kinetic energy of the system T is given by half mv square. Here we have two masses and two velocities, so it is half m1 v1 square plus half m2 v2 square. Now let us substitute the value of v1 square and v2 square. So half m1 x dot square plus 1 by 2 m2 minus x dot the whole square, which we will get, which will yield half m1 x dot square plus half m2 x dot square. We have x dot square in both the terms. Let us take it outside. So we will get the kinetic energy T as half m1 plus m2 into x dot square. Next, let us calculate what is the potential energy of the system. We know the potential energy of the system is given by, in general, it is mgh. For the first mass, it is minus m1 g into x, because the height there is x. For the next mass, it is minus m2 g into L minus x, because the height there is L minus x. The minus is because the masses are acting against the gravity. Then the Lagrangian function L is equal to t minus v. Now we have the value for t and v. So L is equal to half m1 plus m2 into x dot square minus m1 g x minus m2 g into L minus x. So bringing the negative sign inside, we will get L is equal to half m1 plus m2 x dot square plus m1 gx plus m2 g into L minus x. Okay, now let us differentiate this Lagrangian function L with respect to x dot and x. So differentiating L with respect to x dot, we will get dou L by dou x dot. So in L term, we will x dot is only in the first term, so we will differentiate only the first term. Differentiating, you will get 1 by 2 into 2 m1 plus m2 into x dot. So this 2 and this 2 will get cancelled. So you will get m1 plus m2 into x dot. Then dou L by dou x, differentiating L with respect to x. In Lagrangian function L, only the second and third term will be, x is involved in second and third term. So dou L by dou x, differentiating the second term, you will get m1g. Differentiating the third term, you will get m2g into minus x. So it is written into minus 1. It is written as m1g minus m2g. Taking g out, you get m1 minus m2 into g. We know the Lagrangian equation of motion is given by d by dt into dou L by dou qj dot minus dou L by dou qj equal to 0. But the generalized coordinate used here is x, because the motion is in only in one direction. So here x is the generalized coordinate. Writing Lagrangian equation in terms of x, we get d by dt dou L by dou x dot minus dou L by dou x equal to 0. So substituting the value of dou L by dou x dot and dou L by dou x, here we get d by dt of m1 plus m2 into x dot minus m1 minus m2 into g equal to 0. So differentiating the first term, we get m1 plus m2 into x double dot. Again x dot is differentiated again, so we will get x double dot minus m1 minus m2 into g equal to 0. So this second part is taken to the other hand. So m1 plus m2 into x double dot equal to m1 minus m2 into g. Again taking this m1 plus m2 to the other side, we get x double dot equal to m1 minus m2 divided by m1 plus m2 into g. See, this m1, m2 are all constant, so we can write x double dot is proportional to g. So which says that the acceleration of the motion of the Atwood's machine is proportional to the gravity. So this is the required equation of motion of Atwood's machine. If in case the weight of the mass m1 is greater than mass m2, the mass m2 will go down with a constant acceleration. If in case the mass m1 is lighter than the mass m2, the mass m1 will go up with constant acceleration.